is the same functionality as CC1.
Ah, that's
and you just do the same thing with that type passo and equals Intel. You just GCC tag S capital S tag passo equals Intel.
oh, that's excellent. Could you potentially post that into the Discord or a link if you haven't done so already?
And then I'll look into the AS and also I've gotten that part, but AS is an Intel as well.
Yeah, I'll take a look and step through that myself as well.
That was the CC1 not working or not.
Yeah.
Yeah, because I tried to spin up my Ubuntu, got it. I was like, I'm just gonna go use guacamole.
I'll put it in this. Did it work in guacamole?
Yeah, it works in guacamole.
Oh, okay.
Yeah.
So you must have all the.
Distro dependent apparently. What version of GCC? I guess.
No, maybe which version of GCC, but it shouldn't be distro dependent because the compiler should be standard.
Yeah. Well, I mean, like
They might just have some bindings in guacamole.
Yeah.
I mean, it's there. Like if you, so I searched for it in Ubuntu, and it's there. The file's there. You can't call it.
Well, yeah, it's an internal. So
yeah,
it's supposed to be a resource used by the GCC compiler.
Right.
Which
right.
obviously
Normally, no one calls these independently.
Yeah.
Yeah, it's like in the lab. The only reason why you're doing it is to harden that understanding of what's happening to go from source code to your object code.
And see what's produced.
Exactly, so that you have an awareness of that. It's kind of like in 1583, you're encouraged to use all the command line tools instead of a IDE that does all the magic of compiling and running your application by just hitting like a play button of sorts. Oh, really?
Discord, I've been seeing lots of people saying they're using VS Code and stuff.
Oh no.
I've been telling them, hey, you probably shouldn't be, but do whatever your professor says, of course. But
well, fortunately, even if they do that in 1583, they have to hit this course.
Yeah. More unfortunate.
Yeah, and then they'll have to learn it anyway. Okay, so if you're having issues with the lab, please voice that in the inside the Discord. I will probably, definitely, let me strike that word probably. I will definitely go ahead and push that due date out, probably to sometime next week. I haven't decided whether it's Tuesday or Thursday. I might just do it to the next Thursday because this new lab, and I'll make that live pretty soon as well because you'll have access to these lectures. You have access to the book, so you can always read ahead. But the new lab is going to depend on sections 2.1 and 2.2 for you to be able to have the expertise you'll need to start working on it. And so that's what we're going to work on today. So in today's lecture, we're going to start to focus on chapter 2, representing and manipulating information. This can be a pretty dense chapter. My goal today is to get through at least the first major section of it. I think that is a decent amount of data to disperse across one lecture. So we're finally going to get into the next core part of the book. Okay, so let's see what this looks like. So an abstract of what you should expect after reading through chapter 2 is it's going to cover your arithmetic operations. It's going to cover how we can represent our integer data sets as either unsigned values or choose complement numbers, or another way of thinking that is signed values. We can consider what the range of the values can be encoded given the word size and see what kind of impact that has for us. We can consider the effect of casting between signed and unsigned numbers and what effect that might have for us. We're going to cover the mathematical properties of the arithmetic operations as it relates to computational operations versus the truly mathematical operations and see how much in line we can have an expectation of those. We'll show how we can use these bit level operations of C to demonstrate the principles of Boolean algebra. We'll cover the floating point format and how we can actually have that radix point value and how precise those radix points values are. And then we'll talk about some of the interesting mathematical properties of floating point operations as compared to the integer arithmetic operations that we're used to. So this is the learning objectives for this chapter. And of course, the motivation behind these learning objectives is, well, if you want to be a proficient and solid developer, you need to have a solid understanding of how computers do math fundamentally. Like, we really rely on the ALU, the arithmetic logic unit, the mathematical operations to transform and process our data. And with that said, I don't know what's going on with that monitor. Okay, with that said, we should see what kind of after results we might get from that in terms of arithmetic overflow being one of the most common sources of errors that could result if we're not aware of what's happening underneath the hood. And of course, some examples of how this might manifest itself is you couldn't easily replace, or you wouldn't want to replace an expression like this. The evaluation of x is less than 4, right? You might not necessarily, even though mathematically it would make sense that, hey, I can also check x minus y is less than 0. You would think that these would result in the same evaluation. That's not true. And again, because of the possibility of overflow from the subtraction operation, that can result in a value of that expression becoming true or false in a way that you would not expect it to. And for that same reason, we can't simply take the negative of those. And we're going to see why these are the cases in this chapter. So like I said, this chapter is pretty dense. My goal for today is to cover 2.1, information storage, which is broken into 9 subsections. And we'll kind of walk through those over the course of today's lecture. And then the remaining portions of this chapter, so chapter 2. So the first subsection, 2.1, is on information storage. The next subsection, 2.2, is going to really revolve around the integer representations. Then we'll look at 2.3, which is integer arithmetic. And then finally, we'll look at 2.4, which is going to be floating point numbers. And presumably, you've covered these concepts inside of assembly. Did you go really deep in assembly with these, or did you just mention them? Just out of curiosity, like, did you have, what's the volume of lectures you would say you have in assembly leading up in terms of how we represent numbers inside of our computer system?
For spring, I would say out of all of those topics, the one that we covered the most was decimal notation.
Okay, perfect.
The rest we covered, but it was more walking through a program, or walking through code and seeing in the register and all that, and how different operations change values in registers. So like, there weren't any deep dives on other things. I mean, there were 2 complements and unsigned additions, those things. Yeah. Not too much.
Excellent. So hopefully this will be both a review of concepts you've seen before, and maybe a investigation in concept you haven't had a chance to quite scratch. So with that said, let's go into the quick preface here. This is stuff that I would expect that we already know, but we're going to just lay that foundation out. Binary digits, as you know, computers store and process our information represented as 2-valued signals. The reason why that's the case is it's easy to represent, store, and transmit 2-valued signals mechanically, electronically, right? Like, mechanically, we could represent that as a punch card that either has a hole or doesn't have a hole in it. Electronically, we can have a voltage that's either low or high that represents one of 2 values. So there's lots of different ways we can go ahead and represent 2 different states in a physical machine. And because of that, it's really promoted this concept of using a two-valued number system to start encoding our logic and our ability to start processing or representing or modeling data. So because of that, computers use a base 2 numerical system. And of course, the term bits comes from kind of the concatenation of binary digits or binary units. So by itself, a single bit is kind of meaningless, right? It's either just a 0 or 1 and on and off. But its power really comes when we get to group them together and provide context to them. And so when we group them together, it allows us to start being very expressive. We can form a set of unique words that are made of these binary symbols. And then as we develop a context, that context gives us an interpretation that defines the meaning for the various bit patterns. So when we combine those, we can then represent any finite set. And so what we're really going to look at in this, inside this chapter is how we can represent any meaningful set, including the integer values, the floating point values, and even our strings, and our code, in fact, how our code even gets encoded into a binary state. Okay, so we're going to consider the three most important representations for numbers, because that's what we're really going to be worried about when we do arithmetic operations, with a focus on arithmetic overflows. So we're going to look at the unsigned encodings, we're going to look at the 2's complement encodings, and we're going to look at the floating point encodings. And of course, an overflow occurs when we take two valid words, binary words, two binary sequences, we produce an operator on it, and it produces a result that would technically be outside the word size that we can encode into. So the result is still a meaningful binary sequence, but the value isn't what we would expect it to be based off the operation we performed. Okay, let's move on to the actual 2.1 information storage subsection. How do we actually store this information inside of our computer system? Well, first of all, let's mention how we can access binary digits. We stated this earlier, and I'll reemphasize that in this lecture, that computers use blocks of 8 bits or bytes as the smallest addressable unit space. We don't actually have any direct access to single bits. Not to say, now I'm going to make a caveat, but not a real caveat. It's a sidebar caveat. It's not to say you can't create logic that uses single bits. A lot of compression algorithms, for instance, will manage how to effectively build a scheme that allows you to compress as much data into the bit space so you don't have any wasted bits inside of a register of a byte. But that's beyond the scope of this class. But if you ever wonder how those optimizations of compression can work, what you can do is apply logic inside your application to figure out how to fill the space at the byte level to encode meaningful information in the individual bits and use those bits as buckets of sorts. So like you can get really clever with this, but the only way you can get really clever with this if you understand the mechanisms of how it works. Okay, so a machine level program uses memory as just a very large array of bytes. And of course, we mentioned this before, that's called the virtual memory. And every byte of memory is identified with a unique number, right? It's given a numerical value, which is its address, and that's going to be its virtual address space. So in terms of then, once we have those binary sequences stored inside this large array of bytes, how do we interpret those binary digits to have that context? Well, it's the program itself. So in this case, for us, it would be the C compiler that has to maintain that type information so that when it does a lookup for that binary sequence, it knows how to retranslate it so it actually has a meaningful value. Underneath our application, at just the system level, it's completely meaningless. It's just a sequence of bytes. It's just a a sequence of bits that are either zeros or ones. And it doesn't have any understanding of what it is the way we think it does. In fact, it's really up to the developer to give context to anything. Okay. Let's look at the subsection of this for our information storage. And we're going to go a little bit deeper into this concept. So we know that we store everything in terms of binary representation, but we can have different notations on how we represent these binary sequences. So we use a base 2, but there's no reason why we can't take a base 2 numerical representation and then retranslate it, re-express it as a base 10 or as a base 16. So a single byte consists of 8 bits. And so if we want to talk about binary notation, then the range of values we can have. So when we're talking about base 2, whenever we talk about the base, it talks about the number of symbols that you can use in your set of countable values, right? So in a base 2 system, you only have 2 values inside of that counting system. And so we'll use the classical numerical numbers to represent that. So the first countable element would be 0, and the second countable element would be 1. And then after that, we've run out of unique values. And then just like in any other counting system, we can prepend we could prepend in front a more significant digit to represent values more than 2. Or third element. So we can actually have, and that's the same thing in a base 10 number system, right? Like if you have more than 10 things or 0 to 9, you just put a number in front and that represents more elements. So we can do the same thing. So in the case of an 8-bit, then since we have 2 different values, it would actually be 8 digits, it'd be 8 bits long. The same decimal notation to represent the 8 bits would be between 0 and 255 inside of a decimal representation. And then with a hexadecimal notation, since a hexadecimal notation has more countable values than a base 10 system that we're used to, we have to create new values to represent the value of what we would think of as the 10th element, the 11th element, the 12th element, the 13th element, the 14th element, and the 15th element. So we crib from our alphabet and we just grab A, B, C, D, E, and F in that alphabetical order to then assign a numerical value to. So the table here gives a good representation of how we can easily translate between our hex digits, our decimal values, and our binary values using a byte, using the concept of a byte. And this is going to be really important that you feel very comfortable translating between these values. And we're going to look at a couple slides on how we can do that, so that when we start looking at the interaction of these operations on bit vectors, we can have an understanding and an expectation of what the result should be. Okay, so let's talk about hexadecimal bytes. In C, numeric constants, you start with either 0, X, uppercase or lowercase, does not matter. This is one of those instances where cases don't matter to reference a numerical constant. It's the same with the letters that represent our values between 10 to 15, A, B, C, D, E, and F. You can mix them. You can go with all uppercase, you can go with all lowercase. So just know that they're all comparable to one another. Okay, so let's talk a little bit more about converting the bases, between the bases. And some are easier to convert between than others. So if you have a hexadecimal value and you want to convert it to a binary, all you have to do is convert one hexadecimal digit at a time, and the digits can be referred to the same table we looked at earlier. So let's look at an example of this, right? And keep in mind, each hexadecimal value encodes 4 bit values. So it takes 2 hexadecimal values to encode a full byte. And we can see this. So if we have like 0 to F, we could see the appropriate binary permutations on that as going from 0, 0, 0, 0 all the way to 1, 1, 1, 1. Okay, so a quick example, suppose that we have the number, let's say it's 173A4C, hexadecimal value. And if we wanted to convert that, super easy. We look at the 1, and we look at what is the binary representation of that. And we're going to see that's going to be 4 bits large. Each of these are going to be 4 bits large. We would then look at and so that would be 0, 0, 1. Then we would look at the 7, the next one in the sequence, and we'd see that that's 0, 1, 1, 1. Then we would look at the 3 and see that's going to be 0, 0, 1, 1. We'd look at the A, which is going to be 1, 0, 1, 0, the 4, and the C, and find the binary sequence that then gives us its representation. So it's trivially simple, I would say, to convert between hexadecimal and binary. Okay, let's talk about the reverse of that. Let's talk about mapping your binary value into a hexadecimal representation. All you have to do with this is split the binary sequence into groups of 4 bits each. And note, if the total number of your bits is not a multiple of 4, which means you're going to have some left over, then you make the leftmost group the one that is a partial number of bits, and you prefix it with zeros. You fill zeros in front of it. And then you translate each group of the bits into its corresponding hexadecimal value using the same lookup table that we have right here on the slide. So let's look at an example of what that actually looks like. Suppose we have this binary number here of 1, 1, 1. Oh, I'm not even going to say it. It's just, it would be gibberish for me just to spat out ones and zeros. That one of the downfalls of using binary sequences, as you can tell, is that they're too verbose to meaningfully interpret as a developer, right? For us to proofread what's going on, or even to express this, or to store this, even if we were to store this in a file, it'd be way too many values. It would explode just the amount, the size of our file to store this. What's motivated the hexadecimal representation is that it allows us to capture 4-bit sequences in 1 character as opposed to 4. And of course, the reason why we like it better than decimal representations is their binary and hexadecimal are divisible by 2, whereas they're powers of 2, whereas decimal are not. So there's these really kind of janky interpretations you have to do to translate between your binary and decimal representation, which we're going to see in a moment. Well, what we'll see is really hex to base 10 and base 10 back to hex. Anyway, so suppose we have this big long binary string, and I want to retranslate that into a base 16 representation. As we stated earlier, we'll group this into clusters of 4 bits. So we'll start at the rightmost side, grab the first cluster of 4, we'll put it here and see what that translates into. And we're going to continue to do that. So that first 4-bit cluster is going to be 0011, which translates into a 3. The next 4-bit cluster would be 1011, which translates that into a B. The next cluster would be 1101, which then translates into a D. The next cluster is 1010 or 1010, which translates into an A. The next one is 1100, which is the C. And then the final cluster is only going to be 2 bits large, which means that we will then prefix it with 2 zeros so that it's 0011, which is then going to translate into a 3. So our representation of that would be 3CADB3. So again, trivially simple, but the trick here is you have to remember to start from rightmost going to leftmost, and the final cluster has to be 4 digits like all the rest, but you can just pre-fill the front half of it with zeros. Oh, don't want to move that quite. Okay. Now let's talk about why decimal to binary or hexadecimal isn't usually as a why hexadecimal is preference whenever possible over a decimal. Let's try to translate between a decimal and hexadecimal representation. In order to convert that, what we have to do is repeatedly divide by 16. And that'll give us a quotient, and it's going to give us a remainder value. And then we would use that remainder value to represent the least significant digit, because that's what's remaindered out. The quotient represents what's still divisible by that value. So it means we can move on to the next digit. And we keep repeating this process so long as we keep getting remainders and quotients to find remainders on top of. So again, let's take a quick look at what this process actually looks like. So suppose here that I had the decimal number of 314,156. Well, we can convert this to our hexadecimal format, again, by going through the process of dividing it by 16, which is going to produce a Q, a quotient, and an R remainder value. So let's start with the initial value. The quotient when we divide by 16 is going to be 19,634, right? The remainder value is going to be 12. And so we know that 12, a way of translating that into a hexadecimal value would be our C value. Okay, so now the new value, that quotient value we're going to grab, which was 19,634, we're going to divide that by 16, which is going to give us 1,227. We're going to note that down because we're going to have to use that later. But what we care about is the remainder of that is going to be 2. And so that maps easy. It's going to be a hexadecimal value of 2. Okay, so now let's take that 1,227 and let's divide that by 16. Our quotient is going to be 76. We're going to record that for the next step. And we're going to look at the remainder, which is 11, which is going to be our hexadecimal value of B. Okay, now let's take that 76 that we got from the last step, divide that by 16, we're going to get 4. We're going to hold that in reserve, and we're going to look at the remainder, which is 12, and we're going to map that to C, our hexadecimal value. And then finally, we're going to take 4, divide that by 16. That's going to finally give us a quotient of 0. We're going to look at the remainder. That's going to be 4. And so then what you're going to see here is, remember that we were doing this the least significant bit from the first go. So we then would encode this in the order of the last thing we got all the way to the first thing we got. So the last thing we got is the most significant bit all the way up to the least significant bit. So our hexadecimal representation would be 4CB2C. Now, let's look at the reverse of this. Suppose we have a hexadecimal number and we want to translate it into a decimal representation. Well, to convert our hexadecimal numbers to a decimal, we would multiply each of the hexadecimal digits by its appropriate power of 16. Because again, we can think of the digit of where it is as being based off of some exponential power on a base 16 system. So for instance, suppose we had the hexadecimal value of 7AF. And if we want to translate that into the decimal representation, we would take, first of all, we'd create this kind of linear expression that represents the weight and the position in our base 16 system. So we'd have our 16th digit here. So our at position 0, at position 1, and at position 2, we'll have that exponent, and then we'll have multiplied to it our 7, which is the most significant value, our A, and our F, the least significant value. Then what we can do is we can translate this. So the first equation I have is mixed notation, right? So I kept the format of 7, A, and F to indicate that I was pulling directly from our original value, but we have some base 16 values and we have some base 10 values. And that's not good, right? That's a faux pas, right? We have A's and 16s. So the next thing we're going to do is we're going to put everything in the same basis. So our 7 stays a 7, our A turns into a 10, a base 10 representation, and our F now turns into a 15, a base 10 representation. Now that everything is in the same base, I can now perform the multiplication on it. So 7 times 16 to the power of 2, well, let's actually resolve our exponents. So that's the same as saying 7 times 256. 10 times 16 to the power of 1 is the same as saying 10 times 16. And then 15 times 16 to the power of 0 is the same as just saying 15 times 1, right? Because anything to the exponent of 0 is 1. It's the rule of exponents. Okay, so if we then resolve the multiplication, we'd get 1792 plus 160 plus 15. We take that sum, and that's our representation. So you can see there's a great deal more work translating between our base 10 to our base 16, but it's still useful. It's still used. We'll talk about this. I think there's another slide where this is practically used, but try to think about something that's represented as a binary sequence that's practical, that is represented in both hex and in base 10. There's something you're probably familiar with that has equal representation, and maybe you hadn't considered that that's the case. So I'm going to wait until we actually get to that slide before I reveal what that is. Okay, the next thing I want to talk about inside this subsection is going to be our data sizes. So word sizes are something that matters to us a lot, and that's at a system level concept. So every system has a word size. Virtual addresses are actually encoded using the system's word size. So that's why it's a bit of a limitation for us. So a machine that, let's say, has a W, where W is the variable width of our word size, then that's going to translate in having X amount of virtual addressable memory. So our range of addressable memory is going to be between 0 to 2 to the power of whatever the word size is minus 1. So this is why on a 32-bit system versus a 64-bit system, it's going to have high impacts on what our addressable space is. And how much access, how much bytes of access we'll actually have that can be allocated to us as well. So to better define this, right underneath that, you can see there's the 32-bit word size gives us about 4 gigabytes. There's a reason why on older systems, you have a file system that can't exceed 4 gigs. If you ever wondered why that was the case, why sometimes you might have had to like reformat a drive into a different formatting scheme, that's the rationale. The total available addressable space is limited to that. Now, once we go to a 64-bit word size, we have like a ridiculous amount of addressable space. Like, I'd like to think that this is unachievable, but I might be found silly in 20 years, who knows? But it's 16 exabytes. Yeah, that's ridiculous. Yeah, that's insane. That is a lot of data. Okay, so with that said, let's talk about our data types here. So the table below kind of shows the number of bytes that's typically allocated for the different C data types. And we're going to look at this, I think, a little bit in a different slide in terms of what impacts this has on numerical ranges. But here you can just very quickly see if the smallest addressable memory is in 1 byte increments, we can define different types of memory. I mean, we can define different types of numerical values based off of how many bytes they consume. So for instance, we know that a car is a 1 byte, it's a single byte, well, versus say, for instance, a short, which is 2 bytes, and an int, which is 4 bytes, and a long, that's 8 bytes. So this is something that might have been mentioned inside of Java 1, but doesn't really have any practical purpose to you. This is something that probably was discussed a little bit more so in assembly, and it's going to be even more true and more important in systems. Okay, so once we have defined the fact that we have certain numerical types that can consume more than 1 byte of memory, that means that it's a multi-byte object, that the encoding of that data spans at least 4 addressable bytes. So now that poses a new problem to us. That problem is, how do we manage multi-byte objects inside of our memory? So the two considerations that we need to have is, well, what is the address of the object? Like, how do we store multi-byte objects in memory? Typically, it's in contiguous memory in most systems. But then the other thing is that we have to consider is, what is the order of the bytes in memory? So, for example, suppose that you have a variable x of data type int, and we said int is 4 bytes, and it goes into the address space of the hexadecimal address space of 100. And so what I mean by that is, if we took the memory address, if we use that ampersand operator on our x, it's going to return that memory address to us from the virtual memory space. Then we can assume that the address of our object is going to be 100, 101, 102, and 103. We're going to use the smallest. So in virtually all of our machines, our multi-byte object is stored as a continuous sequence of bytes with the address of the smallest address, starting from the smallest address. Okay, but once we do that, the next question is, we know where the start point is inside of the continuous block of memory. But the next question is, what order do we consume those 4 bytes? We know it's 4 bytes. Do we consume it from left to right, or do we consume it from right to left to sequence them to interpret that as an actual value? And so this is a concept that's called endian. Has anyone heard of the concept of endian? So you have little endian and big endian. Does anyone know why it's called endian? Where that nomenclature came from? Oh, you spoiled it, James. Yes, that's correct. We'll get to that slide, but you did give the correct answer on that. Oh no, you didn't. No, you're feel free to spoil. That was a good. It wasn't a guess. That was a good answer. That is exactly the one I was thinking of. Okay, going back to the concept of endian. So, has anyone read the story of Gulliver's Travels? So, and if you haven't read it, it's like a series of small tales of Gulliver as he adventures through this fantasy land. And so there's a subset of the story where there's these 2 warring tribes, effectively, about which way is the appropriate way. They're actually going to war over which way is the appropriate way to open a boiled egg, whether you open it from the little end or the big end. And so this concept where which end of a boiled egg you open it from actually matters brings us the term endian. The endianness of whether you're reading from leftmost or rightmost is that's what it's kind of hearkening to. So a little aside fact for you, so you could think of whenever you see that term, just to know where it comes from. So in our instance, with little endian, the least significant byte, our LSB, we start with the least significant byte, and then we go to the most significant byte. So little endian, and we'll look at an example in just a moment. And then with big endian, we would start with the most significant byte and then go to the least significant byte. So suppose that we had this integer value, which again, it's 4 bytes, called X, and the address space is at 0, it's at 100, it's 100 as the hexadecimal value. And so, and suppose our representation of it is a right here. So it's 1, 2, 3, 4, 5, 6, 7. I have a hexadecimal, I'm sorry, 0, 1, 2, 3, 4, 5, 6, 7. Hexadecimal value of that. So if I want to encode that with big endian at the address of 100, I'm going to take the 0, 1, right, the most significant bit, and that's going to go into that first addressable space. And then the next digits, 2, 3, will then go into the second addressable space. The next set of digits, 4, 5, will go into the next addressable space, and the fourth addressable space is going to be 6, 7. So I start with the most significant bit, and I keep imputing into my memory until I get to the least significant bit. If I were to do this in little endian order, I would start with the least significant bit. That's going to be 6, 7 hexadecimal representation. Then I would get the next least significant bits. That's going to be 4, 5, then 2, 3, then 0, 1. So the big thing to remember here, whether it's little endian or big endian, is that the sequencing of the byte is the same. You don't reverse. Notice, like, we're not reversing 7 and 6. Like, those are tied together. Those represent 1 byte. Every 2 hexadecimal values is 1 byte, but the order is how are we ordering the addressable bytes? So keep that in mind. You're not just inverting the entire sequence, which I think is probably the most common mistake when someone translates between these mathematically, like by hand. Okay, so suppose we wanted to go ahead and show the hexadecimal representation of our bytes or some data inside of C. We can actually author some code. And so here we have an example of some code we're going to make use of when we talk about how to store strings. So just a quick view of this, we're going to go ahead and we're going to include the standard IO header so that we have access to the ability to use the printf. We're going to do a type def for unsigned character pointer that we're going to call byte pointer on line 3 here. And so that way, every time we make a reference to byte pointer, it's type defing to that. And then let's look at some of these functions really quick so that when I show source code in other slides, when we kind of illustrate what's happening in memory, you can kind of think back on this code and say, oh, okay, that's what's going on inside of this function call. Okay, we're going to have a show bytes where we can pass a byte pointer, and we can pass the length that we need to consume for whatever data type that we're trying to express as a hexadecimal value or a hexadecimal representation. Then I'm going to create a local variable called I for I starting at 0 until I hits my length of how many bytes I need to consume. I'll increment I. Inside of my for loop, I will print, and my printf is going to use, right here, we're going to use the percentage sign so that we can go ahead and use that placeholder value. The X value allows me to express a numerical value as a hexadecimal form. And point 2 will, the point 2 will go ahead and allow me to go ahead and make sure it's at least 2 digits long. So that if it was, say, for instance, a representation of a 2, it would be 0, 2. So that it uniformly creates something that looks like bytes to us. And then we'll go, and then what we'll do is our printf also needs to be giving that the actual data that is inserted into that. With printf, remember, it's just like the Java printf. If you use the Java, the system.out.printf with Java. If we use any kind of placeholder or anything with a percentage sign, then we actually have to give it a value to insert there. And then at the very end, after we're done the for loop of iterating over each byte and then representing the byte in the form of a hexadecimal number, we will then hit a new line. So pretty simple function here, right? So keep that in mind for future slides when we invoke it. And then we have a couple other functions that just illustrate how we can represent, say, for instance, an int, a float, or a pointer as hexadecimal values. And so what you're going to see here is if we pass an integer, what we're going to do is we're going to do a casting operation. So we're going to call show bytes, and we're going to pass show bytes we're going to pass the address of the data that's being passed in, and then we're going to cast that into a a byte pointer instead of an int pointer, right? By default, C says, oh, you want this address? Well, the data type that I have a context for is in an integer data type, but we can override that. We can do a cast operation, say, no, I want that address to be translated as a byte pointer instead. So when it goes to advance it, instead of advancing it across 4 byte sequences, it'll advance it by single byte sequences. And then there's a built-in size of operator in C. So I can go ahead and when I pass int, the data type int into size of, it's going to produce the value of 4, right? How many bytes is this integer value encoded in? And so very similar, you could see we could do the same thing for show float and show pointer. It's all the same concept. Any questions with this? Okay, so with that said, let's move on away from the hexadecimal notations and talk about the next subsection with, okay, we talked about how we can represent numbers and then map these numbers into a base as a binary form, and then use that to map it to a hexadecimal form, and how we can retranslate it back into a base 10 form, which is how we think in numbers typically. How do we represent our strings? Well, as we mentioned in prior lectures, to get our strings into bytes, we can encode an array of strings terminated by the null character, which is just the escape sequence 0, which is a 0, 0 in the ASCII code. So each character is represented by some standard encoding. Typically, we use ASCII. And so a representation of this ASCII would be here in this table. And obviously, it's bigger than this. I don't think we've captured all of them, but we captured most of the important ones that you would think of. The uppercase letters, the lowercase letters, and the numerical values with some of the special symbols, like the plus and the slash. Okay, so if I wanted to then actually see how is my string represented inside of memory, inside of a binary state, I can then invoke this function I just showed you, the show bytes function. I'm going to pass it a string literal, and I'm going to pass it the value 6 because it's 1, 2, 3, 4, 5, but then there's the null encoding that comes after it. So there's always a last character that's not displayed, that is your delimiter for your string. And then we could see what the hexadecimal value that will actually be printed will correspond with the ASCII encoding. So as long as we have the context that, hey, this is a character array, we can take each of those bytes and retranslate them back into the letter that makes up that string.
What would happen if we had 5 instead of 6?
Oh, and if we put 5 instead of there, That's a good question. We probably would just print out, we wouldn't print out the null character then, because it's only going to the for loop. Now, what could be more problematic is what if we put 7 there? And so it'll probably just keep printing out and it'll show you your 0, 0, and then whatever garbage is after that.
So in the print function, not a big deal.
Yeah. Yeah, in a print function, that's not a big deal.
Used it in some.
It could be
call or
devastating. It could be devastating.
Especially if you're looking for that null character.
Mm-hmm. Yeah, especially if you need that null character to as your delimiter for processing that string. Because what if you were copying the string over? What if you're making like a copy function and you forgot the null character? Now all of a sudden, any other function call that's using the null character as the delimiter, say your string has ended, no longer has that. And then it'll just keep taking whatever data is inside unless it hits the limit that it has or until it finds a null character, and that's going to become your new string. Okay, so representing strings is pretty it's pretty obvious, I think, since we've already talked about the car data type. Let's talk about representing code, because I think that's less obvious. But since you all went through assembly, maybe it's not so less obvious. So let's start with some code, some very basic code. And again, compiling code to binary isn't universal. That's a portability issue. So I'm going to show you an example representation, some different example representations based off the different systems. And I'm going to try to give you why it's represented that way. So let's look at some an example C program. So consider the following C function. It returns back an int. The label is sum. The parameters are it takes in 2 values, an x and a y that are integer data types. Then it's going to return back x plus y. And that's it. I can actually then go ahead and when we compile that, those instructions generate into our machine code, which have a binary representation. And when I say binary, a byte representation, because everything has to be stored in memory. Our programs have to be stored in memory. Our data has to be stored in memory. So our program instructions that then get fed to the processor on how to execute these actions are going to be represented as a binary sequence. So, and say for instance, you can see inside the Linux 32 and the Windows representations that binary sequence is the same. I'll read it out, but again, this is not something that you would like memorize. This is for the action of just kind of educational understanding. But here we could see it's 55, 89, E5, B4, 45, 0C, 03, 45, 08, C9, and C3. Now, each of those digits have special meaning for our machine code, like our instruction set that makes our processor do something interesting. So, for instance, the 4889E5 is the machine code. It's the binary instructions, the hexadecimal representation that allows us to start moving things between register spaces, right? Some of these other values represent invoking the ALU to create a summation, to perform an add action on values in an address space. So all of this code you see is actually the machine instructions. So when you did assembly, you did this by hand, but you used aliases, right? You use like move, you use like add, right? But that can all be represented as a binary or hexadecimal set of values that inform the processor on what action to take. And so what's happening here is we just take our high-level code and we encode it into the binary sequence that actually has meaning to the processor instruction set. And of course, that's different for each processor instruction set, right? So that would be different from a ARM architecture versus an Intel architecture. Okay, let's move to Boolean algebra. Let's move on. We've talked about binary sequences. We've illustrated how every type of data, including even our program itself, can now be encoded as binary. Let's talk about how we can start transforming binary values into meaningful new results. And so that's done through Boolean algebra. And actually, I have logical here. Let's actually say, let's remove this, because this could either be bitwise or logical, and we're going to make a distinction. On the surface, they look very similar. We're going to differentiate between bitwise and logical operators in just a moment. So here, the simplest Boolean algebra is defined over our two-element set, right? Our binary values of 1 and 0 can also be thought of as true and false. And the operations that we have, we'll use tilde to represent our not. We'll use the ampersand to represent an and. We'll use the pipe to represent the or, and we'll use the caret to represent the XOR, the exclusive or. And so everyone is familiar with these tables. Has everyone seen these tables in discrete mathematics at this point? Okay, I'm going to move on then. So this is pretty basic stuff. So what makes this interesting, though, is just as bits. So this is just bits, right? We have one bit. We interact it with another bit, and it produces some new result. But just like single bits aren't that interesting, single transformations aren't that interesting either. But where the power comes from is when we start applying these Boolean operations onto bit vectors. Because then we can take the context and we can start creating these really phenomenal transformations. So and the way that this works is we can just extend those 4 Boolean operations and work on bit vectors the same way that our linear algebra works on our algebra, or in kind of a maybe even a more basic way than that. So a good mathematical definition of how this might work is given the bit vectors. And so if we express a vector, right, a vector A as a collection of individual bits, and we have another bit vector, and this could be any number of bits long. So if it's an integer, right, that's going to be bigger than 1 byte. Like a bit vector is a more generalized term than obviously a byte. A byte is limited to just 8 bits. So given 2 bit vectors, we can define that operation of A and B as looking at each of the bits in sequence and performing that operation bit to bit in the same in its same hierarchy. So it's important that both of your binary sequences, your bit vectors, are the same size. That's a constraint, right? And so there's all these things you could do, like if you have 1 bit sequence that's smaller than the other, maybe you can prefix all the values as 0 before performing your operation. But that's something you should be considering before you do your transformation, before you do your operation. Okay, so let's take just a basic example of what these Boolean operations on bit vectors look like. And again, you've probably already seen this inside of assembly. So if I took the bit sequence, let's say our bit sequence of A is 0, 1, 1, 0. Let's say our bit sequence, our bit vector of B is 1, 1, 0, 0. Then if I do an and is that operation where if they're both ones, then it's a 1. If it's any other sequence, then it's a 0. So here, that's going to be a 0 because I have a 0, 1. 1, 1 is going to be a 1. At least 1, 0, so the result is 0. Both are 0, so it's 0. Very similar, if I did an OR operation between them, bitwise, I would look at it bitwise, most significant to least significant, 0 to 1, 1, 1, 1, 1, or least significant to, it doesn't matter. In this instance, it doesn't matter, because there's no carryover values. It's not like addition in these instances. If I do the exclusive OR, that's one of those instances where it has to be, if they're both 1 or if they're both 0, then it results in a 0. At least one of them has to be false or 0, and one of them have to be true to result in a true result. So here, that's the criteria for 1. This generates a 0, 1, 1, 1, 0. creates a 1, 0, 0 creates a 0. And of course, the not operation just inverts everything. Simple enough, and probably what you're already used to. Okay, so how do we represent with these bit vectors? Well, bit vectors are powerful because now that we can start packaging things in terms of a sequence of bits, and then we can make these sequence of bits like definable by bytes if we want, but like it's a general term. So if it can be any number of bits, suddenly now we have the power to start representing any finite set. So once we start talking about sets, that means we can start mapping the logic between bit vectors and set theory. We can start defining how these bit operations can do similar things as set theory concepts. Did you all do set theory in discrete mathematics as well? This is
More statistics.
Set theory, and probably in databases too. When you get to databases, which is probably going to be clearly after this class. So there's this concept in that set theory. Okay, good. They surely did. Yeah, there's a concept in that set theory, such as unions and intersections and complements, where like you can have the union of two sets, you can have the intersection of two sets, and then you can have the complement of two sets. And so our Boolean operations on these bit vectors correspond to, say, for instance, our pipe, our OR operation is the equivalent of doing a union, where if I have ones here, you grab the ones from both sets. Our AND operation is the equivalent of an intersection. So it's the only, when they're both triggered at the same time, they're both one at the same time is the only time you carry over that one. And then the not operator is going to be the complement. So whatever's not in this set, but it's in this other set. It's in the outside set of this one. So we can redefine all of our concepts based off of set theory and then re-express them. So say, for instance, if I went back and looked at my example, A ampersand B, then my bit vector can be represented as here, right? The result is this bit vector here, but I can also re-express that as, oh, I took the bit vector of A, and if I intersected that with a bit vector of B, then I have the set of 0 and 6, where 0 and 6 are the positions in my bit vector of where I have ones. So it's another way of expressing the same information, the same data, which can be a very powerful concept when we get to the data modeling component of how to use binary vectors and these operations to transform them into meaningful things. Okay, so let's take a look at a practical example with bit vectors. And this is what I alluded to, and someone had already made the guess. I said there was something that we use a binary kind of vector, a bit vector, to represent that we have common expressions in both base 10 and base 16. And usually you can use either one or the other, and that's color. You can either express color as an RGB sequence between 0 and 255, which is the decimal representation of a byte, or you can use the hexadecimal value for a color. A color can be encoded as a bit vector of RGB. So your red value, your green value, and your blue value. And if you're unaware, you can take the combination of those three primary colors in light theory and produce any color that can then be viewed. So in this example, we just define our secondary values because we want to illustrate in this example how I can use my bit operations, my bitwise operations on my red and my green to actually convert into a yellow. And then it does fit into my bit vector of yellow. Okay, so let's look at the bit level. Let's look at some of the operators on how we now take what we just learned in terms of binary representations and how to do these transformations on binary sequences on our bit vectors, and how do we do that in SID? Well, my bitwise operators for bit vectors are going to be the same symbols we just looked at. So it's going to be a single pipe for or. It's going to be a single ampersand for the and. It's going to be the tilde for the not, and it's going to be the caret for the exclusive or. And that works for any of our integral data types. So we can do that on, say, for instance, our characters. So this is just an example of how we might see all of these in use. I'm not going to spend too much time on that because these are, we already covered these theoretically in the slides, but this is just a showing you how we could take a different, our hexadecimal representation, break it into our binary representation, then get our binary result and retranslate it back into a hexadecimal result. Note, a good note here is when you're doing this for your own understanding, it's good to take the hexadecimal values and translate into binary sequence. So you can actually do the permutations, the computations, and then translate it back. Because it's more difficult to do this left in the hexadecimal form. Because again, you're doing it bit by bit. And again, some practical uses for a bitwise operator is to apply a masking. Because say, for instance, if I had a mask of, say, for instance, 1, 1, and I had some given value here, I could then do the AND operation, which would mask all the values that it would set all the values outside the mask to 0. It masks all the values of the ones that I don't care about. So if I have just one byte where it's all ones, and if I have a byte sequence that's larger than that, it allows me to zero out everything but the least significant bit. So this is a good use case on how this is practical and actually used. Let's talk now. I want to distinguish that from the logical operations. The logical operations produce a different result. So with the bitwise operations, it actually goes, it treats them as bit vectors, and it does most significant, then the next significant, the next, all the way till you get to the least significant. Logical operators result in either just a 0 or 1. There's no gradient between the two, right? So it's I use double symbols to represent or distinguish from bitwise operators from logical operators. So I would use the double pipe for a logical or. I'd use the double ampersand for the logical and. I'd use an exclamation mark for the logical not. And so what that's going to result in, just as an example, is if I apply those in this example, notice the only results I get are either 0 or 1. Right? That makes sense, right? Because 0 represents a false value, a 1 represents a truthy value. And then finally, the operations that I kind of want to conclude our lecture today with are going to be the shift operations in C. And this allows us to shift a number of bits in our bit pattern either to the left direction or the right direction. And so there's some rules you should be aware of. So if I have the expression of X, and then we use the less than, or greater than symbols to represent shifts. So if I have this expression in the form of X and then shift, left shift, I'll just call it the left shift operator K, then that's given X is our bit vector and K is going to be a positive number, which is the number of bits we want to shift to the left. And if we do that, we'll drop off K, the most significant bits, filling the rest behind at the least significant bits for 0. So the fill value is 0. If I do the opposite of that, if I do a right shift, it would take my most significant values and push them to the right and either fill them with 0s or 1s. If I fill them with 0s, that's what we call a logical shift. If I potentially fill them with either 0 or 1s, it's called an arithmetic shift. That's going to depend on if I'm using a sign number. If I'm using a sign number and I'm shifting to the right, I'm sorry, if I'm doing a right shift, I don't want to lose that sign, so I would fill all those values with 1s. So we'll talk more about that when we talk about our integer representations between two complements numbers and our unsigned numbers. And just an example of what this would look like, and I want to say that, yeah, this is the last slide. Just an example of what this would look like is if given this argument here, X, as this binary representation. So if I do X and then if I left shift 4, notice these italicized values are 0 filled. So I'm just pushing the bits towards the left so that the least significant bits now move into the most significant bits. And so here, if I do the right shift, I can show you the difference between a logical right shift and a arithmetic right shift, where on this instance, if my leading term, my most significant term is 0, it doesn't matter. It results in the same kind of shift. But if the leading term is a 1, and that 1's supposed to represent a signed value, then for a logical shift, it just 0 fills, but for an arithmetic shift, it maintains that 1, so it keeps the 1 all the way for the k number of units that I've shifted. Does anyone have any questions in terms of left shifts and right shifts? Excellent, and that's kind of where I wanted to get today, because I figured this was a lot, and I was, I think, right with that. So we're done with the first subsection in chapter 2. If you have any questions, please drop them into the Discord. I'm going to look at the Discord immediately after this class. Yeah, I'm going to post the Zoom student hours in the Discord. I'll make an announcement for that. So keep an eye on Zoom, because I will be posting updates to the lecture videos. So I have I think a couple lecture videos to get posted, and I'll post tips for the first lab, and also post office hour information. Okay, with that said, everyone have a good day.